really concerned about performance. Our main goal with OM was to make a toolkit that was very easy to use, and we just did the most simple implementation we could think of, which was an ASP interpreter for grammars. And that has turned out to be quite slow, which over the years has caused some problems for some of our users. For the past year, I've been working on a new version of OM, which compiles user grammars directly to WebAssembly. This has led to some pretty big performance improvements. It's about 50 times faster on real-world grammars and uses about 20% of the memory. So I think it's been successful. And I think it's sort of an interesting thing to talk about because compiling grammars is in some ways very similar to compiling programming languages. And so there's definitely lots of inspiration you can take if you're looking for optimizations and things like that. But on the other hand, it actually, some of the trade-offs are very different. And it took me a while, I think, to realize that at times when I jumped towards certain solutions that made less sense in this context than they would have when I was compiling a programming language. So just a little bit about me, as Stefan mentioned, I have recently written a book about WebAssembly. It's called WebAssembly from the Ground Up. It's about building a simple compiler of JavaScript that compiles WebAssembly as a way of teaching people about how the instruction set works. And I've been doing freelancing for the past 3-4 years. At the very beginning of my career, I spent 3 years working on the J9 Java VM. Had a really unique opportunity to be part of the team that was building the multi-core memory management framework for J9 from the ground up, basically because J9 was originally a embedded VM, and then IBM had this plan to make J9 server capable. And one of the first things we had to do was get rid of the single threaded popular garbage collector and write something that was a little bit more capable of operating in a server environment. So I think that experience really has kind of stuck with me, and over the years, even though I sort of went on to do much more higher level application programming, really has kind of stuck with me. More higher level application programming team, this implementation level, VM level thing has really stuck with me. Then after school, I had the opportunity to work in a somewhat unique research group called CBG, which was started by Alan Kay, of course, Turing Award winner and creator of Smalltalk. And it was the CBG that we created at home. So I was working together with my collaborator, Alex Worth. He had worked in Alan Kay's research group for several years prior. I created a tool called OMETA, which was another parsing toolkit, parser generator, and created the first version, the first prototype of OM as a way of fixing what he saw to be the mistakes that we made with OMETA. I joined OM, and originally the first thing I did was to work on this visualizer. So I built this visualizer for OM. If you ever work with parser generators, one of the things you may know is that debugging grammars can be a huge pain. And because one of our goals with OM was to make it really easy to use, we focused on the debugging experience. So this is, a live error. I can change the grammar. I have a bunch of test cases here that I can that are checked every time I change the grammar. We can walk through each individual step of the parse to understand, what things succeeded, what things failed. And in working on this visualizer, I actually ended up learning a lot, of course, about how this little prototype works and about peg parsing, and then started working very closely with Alex on OM itself. And over the years, we became the primary maintainer. So we released it as an open source project. And yeah, it's since been used by a few sort of bigger companies, bigger customers. Shopify is probably the biggest user of OWN right now. They use it to drive their developer tooling for their liquid template engine. And as of a few weeks ago, everyone who installs the Wasm CLI gets a copy of OWN for parsing pip required CSV files. And yeah, so the history of OWN, this was originally created to drive our language research at CDG. So we wanted to build new programming languages and design new syntax for existing languages, and we wanted an easy way then to test out these things, to build interpreters and compilers. And that's why for us the focus was very much on the ergonomics of it and not so much on the performance. And it was only sort of once we open sourced the project and people started using it outside of our group, where we started to have these use cases where the performance became a lot more important. So I'm going to jump into implementation details here. If you've ever used a parser generator before, probably most of this stuff is familiar, and I suspect most people are familiar with, context-free grammars, perhaps. OWN is based on parsing expression grammars, which is a little bit different. So I'm going to talk just briefly about things. How many people here are actually familiar with parsing expression grammars? A few. Okay. And it's worth maybe discussing exactly what tags are and where they come from. As the formalism was introduced in 2004 by Brian Ford, if you've been exposed to context-free grammars before, maybe you know that they are generative, which means that they describe how to generate all possible strings in the language, but they don't tell you how to parse the language, actually. So it requires a little bit of artistry to know how to go from a context-free grammar to a parser for that language. Tags, on the other hand, are said to be recognition-based. So that means they really are a DSL or a parser for the language. Superficially, they look very similar, but there are a few key differences with context-free grammars. So the first difference is ordered choice, which Brian Ford in his original paper used a slash operator for ordered choice. In context-free grammars, you usually have operator for ordered choice, non-deterministic choice. What this means in tags is that the alternatives are tried in order, which is like what you do perhaps in a parser, depending on, recursive descent parser. Whereas in context-free grammars, you have non-deterministic choice. It doesn't really tell you how you're supposed to choose between those alternatives. But yeah, in tags, it's like a logical operator in most programming languages, right? It's effectively short circuiting. You try each in order, and you succeed as soon as one of them succeeds. Another thing that's important in tags is that they have reiteration. So something like this could never actually work in a tag. This could never succeed in a tag because, in a regular expression, you could write this because you have non-determinism here, and it sort of magically knows, right, to not consume the last day. It consumes as many days as it can without consuming the last day because that would lead to a parse failure. Whereas in tags, this will simply never succeed. The repetition operators are greedy, and you instead need to use explicit look-ahead to avoid a situation like this. So those are the sort of main ways that tags differ from context-free grammars, and it's relevant because OWN is based on tags. Just jumping back to the syntax then, so this is a very simple OWN grammar for a JSON-like language. Grammars have a name, we have rules in the grammar, so value, objects, members, member. You can think of these kind of like methods of a class. To do a free iteration, you use negative look-ahead. So we need to explicitly say that before we match any character, we want to not match a literal full character here. So this is for a string, right? This is limited by quotes. Ohm uses the bar for prioritized choice and not the slash, but it's still a prioritized choice. And we have cleaning star, we have optional, we have plus, basically all the things you would expect if you've ever seen kind of any sort of formal grammar. Okay, let's dive into the implementation of how we actually sort of create parsers from these user grammars. So basically, the high-level intermediate representation is trees of parsing expressions. So in parsing expression grammar, everything is made up of parsing expressions. Those are the units of composition. So for rule like value, which appears in our grammar, we have so basically a grammar gets turned into a big map of rule name to parsing expression. We have an alternation here for value, which so an alternation succeeds when one of its children succeeds. Here we have a sequence which succeeds only when all of its children succeed. We have an optional in here, and the child is an application of the members rule. We have another rule application here, object. Pretty straightforward. So in V17, the original implementation of Ohm and the version that's is still the stable version today, although we're sort of in a new version that compiles the WebAssembly is in beta right now. So in the original version, we, as I said, we just do an AST interpretation. So we walk, basically, we don't actually generate a parser. At runtime, we parse the user's grammar in, and then when they want to match some input, we then interpret the grammar. And the interpretation of the grammar performs the input matching. And the code to this is very straightforward. This is what it looks like for an alternation. You just loop over all the children and evaluate each child. If one of them succeeds, you can return true. If one of them or if they all fail, you return false. In students for pure peg language is so pegs as defined by Brian Ford. This is like probably 200 lines of code to implement an interpreter for full peg language. We published a couple of papers about Ohm, and in one of them we included the full source code for one of these peg language. We included the full source code. Really simple, really straightforward, but it's not very fast. And maybe for a lot of people here, that's not too surprising. Maybe some historical context, the number one performance wasn't our first concern when we originally wrote this back in 2014. The other thing is that at that time, JavaScript JITs were showing so many performance improvements year over year, and we had a sense, we should just write our code in the most straightforward way, and the JIT will make it really fast. Turns out that JITs don't really optimize for the shape of interpreters, but lesson learned. So being a team that I've been working on for the past year, the idea is instead to turn it into a true parser generator and actually compile these grammars to a WebAssembly module. So the compilation process, basically we use the same high-level representation. We're still walking over a P expression tree. Process, basically we use the same P expression tree. It's very similar. We're still overall children. Emit the child. Have a conditional jump to the end of the block. If one of the children succeeds, etc. There is a slight difference here in that, you may notice that we have this is, maybe not always exactly what's going on here. This is JavaScript code, and I have here a little sort of macro assembler library that emits the WebAssembly, so all the calls that begin with ASM are actually emitting code, but this is a runtime loop. So we're just unrolling the loop with all the children there, and this kind of code is flat. Then we have sort of a block. In WebAssembly, all control flow is structured, so if you want to have jump, you always need to be inside either a block or a loop. Blocks are things that you can jump to the end of, loops are things you can jump to the beginning of. But yeah, the general approach here is very straightforward and simple. We just, we unroll the loop and make all the code for each individual expression. There is really, in the WebAssembly module, we basically have a function, a toggleable function for every rule in the grammar. And within that, we just inline the code for all of the individual parsing expressions, with the exception of rule applications. So these are generally a call to the corresponding rule. And that means that, parsing expressions on their own don't tend to be very deep. Right, so these are all going to turn into calls, but this turns into a loop. This turns into a loop. Yeah, so we don't have a huge function logics or anything. It's a very straightforward approach to emitting code. And yeah, so the first version of this, again, pure peg language, so Ohm adds some features to pegs which were not in Bytefor's original definition, which complicate things. The pure peg version of this took me about 8 days and was already, I think, 50 times faster. So I was very excited. But I hadn't yet tackled building any kind of parse tree or, as we call it, concrete syntax tree, which is obviously something you need to do as well. And I also didn't tackle any of the old specific features. We have a number of features which are a little bit trickier to deal with than pure pegs have. One of those is memoization. So I'll get into some detail about this later, but Ohm requires memoization to support left recursive rules, which are something you would like to have if you want to have left associative operators. We also support parameterized rules. Again, I'll go into details about this. And implicit case skipping. And these are sort of three things that not only require adding a lot of complexity, but also sort of has some performance challenges. So as I implemented each one, sort of the amount of speed up that I was getting went down and down and down until I kind of plotted back piece by piece. And so let's talk about CSV building. This is very important, if you're actually trying to parse. You don't just want to recognize input. You don't just want to say, yes, this is valid JavaScript, or no, it's not. You want to do something with that input, which means you need to build some sort of parse tree, concrete syntax tree, abstract syntax tree. And the difference between those two are maybe not all that important, but you need to build up some representation of the source code. And this actually is surprisingly a lot of interesting performance lessons came out of the CSV building process. With your CSVs, there are two concerns. One of them is you want them to be fast to build so that they don't slow down the parsing process. But the other concern is that you want them to be fast to walk. So that you want them to be fast to walk. There's little points, at least for a lot of use cases where Ohm is used, there's little value in being able to quickly parse if the walking time takes 10 or 50 times as long to sort of process the tree. And, if you're doing linting or syntax highlighting or something like that. So the approach I took for CST building, so the first kind of question, so OM is a toolkit, for JavaScript and TypeScript, but now that we've compiled to WebAssembly, the first question is, where do you allocate your CST nodes? So WebAssembly has linear memory, which is, you can think of it as just a big array of bytes, basically. And within linear memory, by default, you use 32-bit offsets rather than machine word size pointers. And what's nice is that with a CSP, you have, so one option would have been to heap allocate CSP nodes, right, like direction collector manage them. We could do this from within WebAssembly, so WebAssembly now supports GC, and so you can actually allocate from within WebAssembly, allocate GC managed objects. But it's interesting to use arena allocation in Wasm linear memory. So what's nice about CSPs, right, is you have a bunch of small objects which all have the same lifetime. Basically, there's little meaningful use for having some of those that live much longer than the others. So this is perfect for arena allocation. And then I can do really fast, just bump allocation into Wasm linear memory. And there was also nice areas where we were able to use a flat representation. So this is, I think, something that seems in the last 10, 15 years, people have come around to when it comes to designing ASTs and CSTs, that you don't want to have a memory managed object for every node with 64-bit pointers between them that uses a lot of memory, gives you a lot of fragmentation, and instead we are just allocating them linearly into Wasm linear memory. By virtue of using WebAssembly, we already get this sort of pointer-free representation because, as I said, in Wasm memory by default you have 32-bit offsets that you're dealing with, not full 64-bit pointers. So we have 4 node types that we have to deal with. So we have terminal nodes, which represent just when we're matching some kind of raw text in the input. Non-terminal nodes for the rule applications. Then we have list nodes for repetition operators and optional nodes as well. You could lump these together and say that they're all sort of forms of list node, right? Optional is just 0 or 1. But we decided to keep them separate. And just to give you an idea of what the typical distribution looks like, this is just one sample, but for a 14K input file, we have about 12,000 terminals, so roughly 1 per character in the input. About a fifth of that are non-terminals, and then another fifth or so are list and op nodes. So then when it comes to performance, right, the main focus is to make these terminal nodes cheap. And yeah, turned out that was sort of fairly easy to do. There's a number of approaches actually that we can do this with, but a simple one is to use just tagged I32 values, so to not actually allocate any sort of separate memory in our, not allocate really a true CST node, but where the pointer would be, instead just use this tag value. And because for terminal nodes, all we care about is how much of the input needs to be skipped over. There's really nothing else that needs to be saved, because the characters themselves can be fetched from the original input. For all the other CST nodes, we have basically this 16 byte header, and then potentially a list of children, which are, you could call them pointers, but in WebAssembly, they are I32 offsets. And to give you an intuition of what this looks like then when you have a tree and how this maps to linear memory, so you're always going to be sort of allocating children before the parent. You have sort of a post-order traversal order in linear memory, with the exception that I haven't talked yet too much about backtracking. This is something also that you have in pegs. So in, say, an alternation, as you try individual expressions, right, you might advance the input, and the expression may fail before it succeed, or it may sort of encounter a failure before it can consume everything it was meant to consume, in which case your input will backtrack. And you can have dead nodes, basically garbage, that gets allocated for the expression that was partially matched. But otherwise, we have a pretty nice sort of post-ordered traversal in memory. And it would be interesting, I haven't done this yet, but there is something interesting here about leveraging this order in memory during the walk phase. Right, of potentially, because a lot of things you want to do are bottom-up traversals anyways. And so there would be something interesting to do here to actually just, rather than walking the pointers in the tree, to actually just walk through linear memory from low to high, but I haven't experimented with that yet. So yeah, bringing it back to sort of all the things I had to get before this was done, right? So that covered CST building. And then I had to start tackling the OHM specific features. And so one of these was memoization. In the title of my talk, I talked about Packrat parsing. So parsing expression grammars are really nice and convenient. One of the great things about them is they're very expressive, and this backtracking ability that they have lets you do what you can think of as unlimited look ahead. But the problem with that is that it can lead to exponential parse times. So you can have rules, right, that do a lot of work to parse almost the entire input. And then at the end of a sequence, you might be expecting a semicolon and you don't have one. And then you backtrack and sort of undo all of that work. And a further rule could end up matching many of the same rules and doing a lot of the same work over and over again. So yeah, Brian Ford also coined this term Packrat parsing for his approach to dealing with this, which is to simply memoize all of your rule applications. And the way this works out, so this is just two different ways of representing the what we call the memo table in a Packrat parser. But the intuition is that you have a column for every input position and a row for every rule in your grammar. And if you try a rule at that input position, after it completes, you then save the results, whether it's success or failure. And this gives you guarantees linear parse times, but you can have a very high constant factor because this uses a lot of memory, right? So if you think of some of our grammars, sort of real world grammars, have on the order of 200, 250 rules. So that would, if you had even 4 bytes per rule, you would have 1K per input position. So, an 1,000 times factor memory usage just for this memo table. So this can get very expensive and has a huge impact on performance. So yeah, one of the next things I needed to tackle was to figure out a way to deal with this. The good news is these memo tables are very sparse in practice, so most rules are not tried at most input positions. And I adopted, what I call a block sparse memo table representation. And in the literature, I mean, I don't think there are different variations on the same basic idea. I don't think I've come up with anything novel here. But what we do is to just break the memo table entries into blocks of 16 slots. And so we eagerly allocate the pointers to the blocks, but lazily allocate the blocks themselves. And this vastly reduces the memory usage to the point where it is not a concern for performance, and on typical input sizes is not a concern for total memory usage, heap size either. The other thing is to sort of find a good way of using the memory that we do have for the memo table. It's a little bit more complex than just success and failure. So, and especially in GNOME, because some of the features we include. But so in this memo table, we can either have a pointer or an I32 offset into Wasm linear memory with a low bit set. So these are always 4-byte aligned, at least, if not 16-byte aligned. So yeah, we can use the low bits to tag these values. So the actual success nodes have a low bit of 0. When we have a failure, we want to record the failure, which we use with a low bit of 1. But I won't get into the details of this, but for error reporting and pegs, you also need to basically, throughout the parse, track the furthest input position that was read, because that usually is where you want to report the error. So we need to track this pretty ubiquitously, and that also adds some overhead. But we just store that in the upper 31 bits of the tag value. And another feature that OM supports is implicit space skipping. We have a user-level spaces rule that can be overridden. So by default, it's ASCII space characters, space tab, etc. But it's common to override this rule to include your language's comments as well. You generally want to treat those as spaces. And so that means that if we treat these naively, they will end up using a fair amount of memory and causing performance problems, because real-world inputs are filled with spaces. And most of the time, you do not care about the parse tree for the spaces. So we have an approach where we just encode spaces with the 2 low-bit set, and much like with terminals, we just record the match length, and we do not actually build a CST node, and we just lazily materialize those if they're required during the walk phase. The next thing I had to tackle was parameterized rules. This is one of the examples where I think my intuitions about compilers for real languages led me astray. So an OM rules can have parameters, and the way this plays out, so the parameters can be basically any parsing expression. And here's a simple example of where you might use this. Again, sort of thinking of JSON-like syntax, you could have a rule called keyval that would say it takes 2 parameters, a key expression and a value expression, and it will match first the key expression followed by a colon followed by the value expression. And here's how we could use it with another rule called ID fields. And here, the syntax is slightly confusing here, but this is a terminal expression, so surrounded by quotes. And in the input, we want to match a literal quote followed by ID followed by a quote. So this is a terminal expression, and then our other parameter here is a application of the number rule. And so you can think of these like, but even more specifically, you have to think of them like lambdas, actually. So, if you look here at the call site, basically, the call site, the only thing we can do here is evaluate that parsing expression. And we basically want to be able to generically eval whatever those things are. So they're very much like lambdas. And in the original Ohm implementation, we actually dealt with parameters using an actual rule stack, which is very much like a call stack. And it's kind of interesting because once you have parameters, the Ohm language starts to look like a very simple kind of functional language, maybe. And yeah, the first version that I implemented of this, I actually did lambda lifting, and whenever an expression appeared as an argument, I created a new top-level function in the Wasm module for that thing. And then in the body of key val, I can just always emit calls for those. But that adds some complexity that actually wasn't really required. So yeah, this is one of the places where grammars are very different from a real language. The biggest grammars we have are kind of 500 lines or something. And WebAssembly maintaining this rule stack is something that I would have to kind of separately maintain. So in WebAssembly, you don't actually get access to the call stack. And so if you need to maintain information like this, which sort of has a one-to-one correspondence with the call stack, you need to maintain a shadow stack. But then I realized there is a much simpler solution here, which is to just do static specialization. And just expand all of these at compile time. So for every unique combination of parameters, I just create a new top-level rule that is specialized for those parameters. And that means that at runtime, there are no parameters. It simplifies the runtime semantics, simplifies memory management on the Wasm side. It means I don't need to deal with Stack Overflow on the shadow stack, or growing the shadow stack, or anything like that. And the other thing is that this works very well with memoization. So one observation about parameterized rules is that it complicates memoization because, if I try this key val rule at position 0, I can only reuse a memoized result if it had the same parameters. Otherwise it's actually doing something different, and it wouldn't be valid to reuse the memo table entry. And by doing the specialization, then, that it meant that memoization was very, very simple, because every top level function basically could be memoized based on its offset in the module. Yeah, and just one last Ohm-specific thing that I had to deal with that also had some pretty big performance impacts was the implicit space skipping. So in parser generators, this can be kind of a pain to get right? There's a lot of often, if you see the official specs for languages, you'll have a syntactic grammar that, the syntactic grammars ignore spaces. The lexical grammars need to deal with them. Pegs are generally scannerless, which means that you don't have a separate tokenization phase. You deal with everything in a single grammar. And this means that if you're porting if you're looking at a language spec and trying to implement an own grammar for it, one of the things you will have to figure out is where are all the places that I need to manually skip spaces. And that can be quite painful. So we have this implicit space skipping based on whether the rule begins with a capital letter or a lowercase letter, which seems a bit, maybe subtle, but turns out to be quite convenient in practice. And yeah, just very quickly, I mentioned most of this already, but the naive way to do this would be to actually allocate the full sort of subtree of CST nodes for all the spaces. And instead, the optimization was to just store the match length. And then during the walk phase, we can actually lazily materialize the CST nodes if required. So there are some cases where, say you have comments that have some metadata included in them, right? So linters commonly have, use comments to control. You can control the linter with comments. You may actually want to inspect the comments. In that case, we can, during the walk, call into the function that parses spaces and actually produce a proper CST. Okay, I want to so that kind of covers the core implementation. That was where, most of that was the things that I needed to do to simply get this thing working. I talked about some of the optimizations that I did. I want to talk about a few more of those. I like this line from Ken Dybvig, the creator of Shea Scheme, who said there's a fine line between optimization and not being stupid. So I think of this not as an optimizing compiler, but just as a not stupid compiler for pegs. And some of the not stupid things that I have implemented that have given us some pretty big gains. So I think doing the specialization of the parameterized rules was a big one. Inlining has, unsurprisingly, kind of also led to a lot of gains. You get in pegs and in Packrat parsing, you get kind of a double win from inlining. Not only do you save the call overhead, but you also save space in the memo table, because if you inline something, then you don't need to memoize it. And especially single-use rules are things which provably do not benefit from memoization. Another thing was in building the CST, there's actually a lot of nodes which are structurally identical. So you have, for example, say you have a rule like digit, which consumes a single character. So you would have a non-terminal node that identifies its rule ID as being digit, but it will always consume a single character. So in the tree, you don't need 100 different nodes or 1,000 different nodes that are separate copies of the same data, but you can pre-allocate them. So this was also a big win, especially because a lot of these things are in the leaves of the tree. So you have, a pretty large gain in sharing them. And I've started to go into sort of some basic kind of micro-optimizations, I guess, sort of pattern, optimizing certain patterns. So a common thing in pegs is to do this sort of, as long as the next character is not a quote or whatever it might be, consume anything. And so you can sort of replace the naive implementation of that with something which is a little bit faster. There are other things I would like to do here that I think would be interesting. Some of them are the kinds of things you would do in any sort of optimizing compiler. Some sort of cost-based inlining would make sense, I think. And you do have, in grammars, you have something that's kind of like common sub-expression elimination. You have sort of common prefixes. So in an alternation, you may have choices which have common prefixes. So it's kind of fun sort of looking at sort of the standard optimizations you would do in a programming language and thinking about which ones make sense in grammars and which ones don't. I've even thought about doing whether you could do something like inline caching in grammars. It would have to be something that looks very different. What's relevant is what's ahead of you in the input stream at the point that you go to evaluate a rule, right? So that would have to play into it. Yeah, so I think there are still more optimizations we can do here. But to just sort of paint a picture of where this got us to, so the grammars that we're benchmarking against, so one of them is Shopify's grammar, because as I said, they're sort of the biggest user of Ohm, versus previous version of Ohm were about 56 times faster. We have an official ES5 grammar, which is about 40 times faster. And to benchmark against, a hand-optimized JavaScript parser, this isn't really apples to apples because Esprima is building an AST and not a CST. But just to sort of have a ballpark idea of where we are. So, Esprima is still about 3 times faster. Like considering that's a hand-optimized parser, so our grammar is not at all, the grammar itself is not at all optimized. It was just sort of written to have eyeball closeness to the ES5 spec. I consider this to be a pretty good result, that we're within an order of magnitude of a handwritten and hand-optimized JavaScript parser. Another interesting comparison is Python. So Python 3, some people may know, is now based on parsing expression grammars. So Guido did a few years ago, kind of went through a lot of the things that I talked about today. Sort of, he has a nice series of articles about implementing pegs. And so we can benchmark sort of very roughly against the CPython. So this is a grammar that's generated from a peg, but it's generated C code. And it also uses memoization, but like Esprima, it's generating AST. And we're in the similar ballpark of being about 3 times slower, but again, I consider that to be pretty good. There was a few more things I wanted to put in here, but I guess my slides didn't get regenerated. The main paper that I want to call out is of related work here, so I don't think anything I've done here is especially novel. The classic paper on fast Packrat parsing is Robert Grimm's Better Extensibility Through Modular Syntax, which is about a system called RATS, which is very similar to Ohm, although some of the Ohms, I don't think it includes sort of any of the Ohm-specific features, so support for left recursion or parameterized rules. But many of the optimizations that I talked about, he has talked about as well, including sort of the optimization for the memo table and some of the others. So that is really kind of a whirlwind tour through Ohm and the new Peg to Wasm compilation. And I would be happy to take any questions that you have, assuming we have time. So thanks.
Okay, well, a question that a great talk. My question is regarding the optimization of the memoization paper. So it seems to me that a lot of this, you already mentioned that it's fast, but it seems to me that there is a locality that is induced by the grammar. your example with the expressions is perfect.
Yeah.
If you were like, if you were to analyze this, you'd see that there are kind of like strongly connected components or temporal aspects that you could use. Did you look into this, or are you aware of any related work in that area?
I haven't looked into it. I've also, thought about that. There's also an interesting, so at a given input position, there is a locality thing, and also in adjacent input positions, there's often a locality thing, right? If a rule matches, like expression, if it matches at a given input position, it's probably correspondingly lower chance that it also matches at the next input position. I haven't tried it yet. I think it would be super interesting. One thing that I had wanted to try there would be a shared table. So perhaps having a shared memo table where you have a single table for, say, 4 input positions. But I couldn't convince myself that that would actually be a win, because then I would need to record in the table itself extra information about which input position it refers to.
But you could go away from this like 16 insult thing, because then I think if you had this information about which kind of grammar trees you would see frequently, you would go away from this 16 block.
Yeah.
So I think this is the way to go, is to just go away from this static 16 block allocation more towards what you would see from, and this is purely grammar based.
Yeah. Do you think are you thinking static analysis then, or?
Yes. So essentially, when you compile your Packrat grammar or your Packrat grammar into, or your own grammar into Wasm, you would do this analysis, and they could indicate to you where most of the variation is going to be.
Yeah. Yeah, it'd be interesting. I think. I guess intuitively, I'm not sure how much you could figure out statically versus doing something like profile guided optimization, perhaps, right? To give sort of the grammar author like, okay, we build the first version of the grammar, now run it on some representative inputs, and then we'll give you tuning parameters that can make it more efficient. I think it would be very interesting. I mean, I'm sort of convinced there's this whole missing, there's surprisingly little academic work about stuff like this. And I personally find it super interesting that you could analyze all the different things that we've done.
That's a big question. Does anybody but Stefan? Go ahead.
So I'm just going to rephrase what my PhD advisor said. There is no work to be published in parsing. So I mean, like the only paper I know that was Packrat Parsing like in the early 2000s.
Okay. Well, we published 2 papers on this. So yeah. An interesting one, by the way, I should mention that we published is on incremental Packrat parsing. So one of the nice things about the memo table, we were kind of surprised that no one had done this, but if you're saving all this information, it would be nice if, for use cases like syntax highlighting in editors, why would you parse the entire inputs, and then when the first line changes, throw away this memo table and then, recreate it. And it turns out that it's relatively simple to just record a little bit extra information and then be able to use the memo table for incremental parsing as well. So that would also be a follow-up on the WebAssembly stuff. I have not yet implemented the incremental parsing. So we have OHM v17 has incremental parsing support. I'd like to do it for v18 too, but haven't done it yet.
So did any of the optimization decisions you made influence the desire to provide some interesting tooling or useful tooling? So was also available in things that you now can't do anymore?
Not yet. I would say the tooling, so in the process of writing these optimizations, I certainly found myself, wanting better introspection abilities into, where the time is going. And that would feed back into tooling, I think, that would be useful for users. But I think I was mostly, because we spent most of the past 10 years focused on things that were mostly about the ergonomics of home. The past year on the WebAssembly stuff was mostly focused on performance, kind of me getting out all my performance desires that I had been sort of pushing down for a while.
My question is regarding the parameterized rules. Your approach is to expand the parameterized rule in advance. I'm afraid that that approach doesn't work for the recursive parameterized rules.
For recursive parameterized rules, that's a good question. Yeah, I don't think I have encountered it. Are you thinking of left recursive or recursive in general?
The table on the left-hand side here.
Yeah, I probably need to deal with that and haven't got it in any of our test cases currently, like in any of our existing grammars. It's a good point, yeah.
All right, I think now it's time for the coffee break. So, Patrick, thank you very much for your talk.
And if anyone wants to talk about this or about WebAssembly, there's also sort of some fun stuff about managing the WebAssembly memory from JavaScript that I'd be happy to go into. So yeah, just come say hi.
We are back in half an hour.
So we went directly from an AST interpreter to compile into WebAssembly. Yes.
Did you implement the bytecode interpreter?
Oh, I did. Yes. Sorry. Yeah, my original
master.
Yeah. Which I think. Yeah, I mean, I had some
believe the legitimate compilers, especially something like DA, but also they're just so free to so that they can compile AST reasonably well. I mean, not as good as if you actually were out of way things, but they really struggle with this bytecode. So actually, it's just not effective. They expend time.
Yeah.
So you have these register locators that are typically linear scan, and then the bytecode is the worst case.
Yeah.
So in that sense, the AST interpreter is probably the fastest you can do without producing your.
Yeah. I mean, we could have also JS code.
Right.
Which I think Alex did with a previous version of that. For some reason, he was convinced that was not a good way to go. And when I first got involved with him, I didn't have any sort of intuition myself.
So do you have the ability to interact with JavaScript? So did you ever experiment with creating JavaScript instead of, I think AST linear memory is faster, but create directly JavaScript.
No, I mean, my intuition is like, I think you don't want, and I mean, I've seen this in profiling, that you end up with a lot of time. I mean, a lot of time spent scanning the CSV notes.
So how people use like the do they cross create aspects of this or do they
Depends. So we often just directly process the CSV. I think a lot of people create ASTs because they think the AST guys. It's sort of funny, we have this. At some point, we added this like helper method to AST, even though sort of we always had this sort of pretty convenient way of walking the CST. We generally use that for everything. We have this helper method of to AST. It was intended for like, oh, if you really don't want to put any thought into what you're going to do, how you're going to process this, we'll create sort of an AST, but of course, you can't automatically create an AST because you don't know which things are relevant. But so many people end up using that simply because I think they have it in their heads that like an AST is what you need.
Yeah, I mean, that's what we tell them when they go silent for us.
So I saw some interesting things like this. This walking of the CST, I actually even saw that, so we have sort of this raw CST in Wasm linear memory. And then the first API that I tried for this is to materialize, like to create sort of JavaScript facades, like flyweights or what. Forget the design patterns, but you know what I mean, right? Like create a heap allocated object that's just backed by and it's simply the allocation overhead is surprisingly high. And then I created a new version that where it's just you like I use handles for all the nodes and functions that can fetch the fields from a handle. And it's like literally 10 times faster. Which I still find kind of shocking. I mean, well, about like
application is cheap, but that's not that cheap.
Yeah, still though. I mean,
you have to initialize the objects and stuff.
Yeah, I know. I mean, I worked on memory management. My intuition is still that, like, I guess I spent so many years defending garbage collection.
Mostly bad.
Yeah. Yeah. So I've been trying to figure out sort of like what a clean API is to be able to do this like really fast walk, because if you allocate JS objects for every node, then I mean the thing I've been benchmarking on is unparsing, so reconstructing the original input from CST, which is a relatively heavy test. But then you end up having sort of a 10-to-1 difference between parse time and swap time. But whereas with this faster handle-based approach, where we don't actually create any heap objects during the walk, it's more like 1 to 1. Yeah.
Which is physical problem, because we had a couple of people who were like, oh, well, looks like going to be in the States.
Do you want to look at that, or?
Wants to go to the States now. So trying to jump ship.
Do you actually like bypass the garbage collection by?
Yes. Yeah. So in WebAssembly, you get basically a byte array.
This year
you manage yourself. It's bounds checked, but otherwise you can manage it yourself. And if you have a C++ app that's compiled to WebAssembly, it's going to be using a malloc implementation, which is allocating memory out of this WebAssembly linear memory. And before Wasm GC, so the GC spec is sort of a new part of Wasm, but before that, if you wanted a garbage collected language on Wasm, you would ship GC code as part of your Wasm blob that is managing that same linear memory. So basically, you can do whatever you want with that. I mean, it's typical, like if you're writing a Rust app, the Rust allocator is then allocating out of there. But you can also just, so I'm just kind of doing bump allocation myself onto this into this memory. It's basically like from the JavaScript side, you can access it like a typed array of whatever bit you want, and the garbage collector does not submit. It's just virtual memory that. So you use so there was all these APIs that were added to JavaScript originally for WebGL. The typed array. Are you familiar with these? Typed arrays?
Not really. Like I just know some basics of JavaScript.
I mean, I can show you the code if you. I can show you. This is the CST read. It's like nice, fast. So on the JavaScript side, you have this data view object. Basically just JavaScript. So you have a data view, which is just this class that, has a backing buffer, a length, and you can just say, you can get any big width you want, and you can say little endian or big endian.
Okay, yes. So you actually get the printers from.
Exactly, yeah.
You can use it to build your own, basically your own runtime or whatever.
Exactly. Yeah. So and one of the fun things about WebAssembly, so I like, it's very peculiar, but I really like working in JavaScript with WebAssembly because you get this really unique combination of kind of doing low-level stuff, but when you get things wrong, we'll tell you, kind of, right? So you have bounds checking on your memory, which is bias. WebAssembly has pretty robust validation, so if you screw up in your code gen, you'll often get an error from the validator. And it's just like very pleasant. It's a very pleasant way to do kind of what feels like low-level programming, but
we see this pattern like all over the place in this arena of course. So you even like in computer games like compilers, garbage collectors.
Yeah.
Yes. So just chunk of memory and just place like objects like just like a stack and just bump the pointer.
Yeah, exactly.
And when you're done, you just either like read the whole thing, or if you have this like transient lifetimes, then just have linked lists of these arenas and do the same thing.
Yeah.
And it's a really efficient pattern to manage them.
Yeah. I mean, one of the things I worked on too when I worked on the JVM at IBM was I don't know if you've ever heard of RTJ, real-time Java.
No, I haven't. Even though I work for Oracle, I haven't.
Yeah, so I mean, I don't know if it's still a thing, but it was a set of extensions to Java that was, to be able to do soft real-time stuff. And one of the big things you need to deal with is, the garbage collector, is it going to pause? And they used a form of arena allocation. So you have these scoped memory spaces, and your thread can enter a scoped memory, and you have to exit them in stack order. I think it's going to come back, right? I think we're probably due for, we've gone through these phases of 20 years ago, it was Ruby, Python, etc. And then the last 10 years, everyone's like, Rust, and maybe Go. Hey, I'll come by. Do you also have a coffee break now? Or?
Yes.
Yeah.
Yes. If you can join the coffee, maybe we should go.
Yeah, we should go. So I think
I'm not entirely sure how smart it is. There are students around.
Oh. Yeah, like I personally think we're due for another kind of round of, realization that maybe all the lifetime stuff that you need to deal with in a language like Rust is not what you want to be doing for everything, and that you need more of a balance between, the ability to choose which memory management techniques make sense for the workload, which is not very easy in most languages. Okay. Disagree?
I think which one is
Oh.